So in this set of lectures, we will cover how to solve PDEs using spectral method. Okay. So the basic idea is that we have this PDEs. We have this PDE. This PDE. So left hand side is, so phi is function of x and t. So we are working in 1D. Phi is function of position and time. Now, so the evolution of phi is given by this equation, partial phi partial t equal to some function of phi, first derivative of phi with x and second derivative with phi of x and time. Okay. Now, so this is parabolic PDEs. We'll skip the details on that part. We'll just focus on how to solve it using spectral method. Okay. Now the idea is that we expand phi in real space as Fourier series of Fourier transform I t for I k x. Okay, is 1D, so k is a wave number. Now it's of course in a box 0 to L. So k is discrete. Okay. Now when we substitute it here, using the fact that e to the power ik forms a complete basis, we get equation d by dt of phi kt. And the right hand side will be some, it's again kt. Okay, so it's Fourier transform of this whole thing, and of course it depends. It can be the complex function, but it is Fourier transform of the right hand side. Okay, and once we have this Fourier transform, then once we have this equation, then we can use any of the methods described before. For example, Euler method will give us phi kt plus delta t equal to phi kt plus delta t times f hat kt. Okay, so we can easily get the next time step. So given initial condition, which will be phi x at t equal to 0, we compute phi k at t equal to 0. Of course, set of phi k's. Okay, so there is a set of phi k's, and then we get equation for each phi k. So please remember that we'll have lots of equations. For every k, there is a differential equation. This one, every k. For every k. For every k. So we get equation, and we just solve this set of equations. So we have set of equations using any of the methods, Euler, RT2, RT4, Adam-Bashforth. Okay, so here of course we'll need the initial condition for each of these differential equations, and we will just use it. I mean, we'll get the initial condition for phi k's from the phi x at t equals 0. Okay, so that's the basic idea, and we know that the derivatives are very accurate using spectral method. So this is very useful for getting accurate PDE solvers. Okay, so for weather prediction, this is in fact one of the methods, popular methods for weather prediction. All right, so let's look at the PDEs which we will discuss in this course, and that will be diffusion equation, wave equation, Euler's equation, Navier-Stokes, and Schrödinger. Okay, so these are the equations which we'll cover in this course. So let's look at diffusion equation, which I did in last class, but I will cover it in some detail. Okay. So diffusion equation is this. So d phi, so it's a time derivative of phi with okay in the left hand side, and right hand side is kappa d square phi dx square partial. So kappa is a constant, and kappa is called diffusion coefficient. Okay. Now, if I do the Fourier transform, it's just straightforward, which we studied in this set of chapters on the Fourier transforms. So Fourier, so this equation in Fourier space appears like that. So in fact, it's D is not is total D. So is a for there are of course lots of wave numbers, and for every wave number we get left hand side is d by dt of phi k. So which is function of time. Okay, and right hand side is minus kappa k squared phi k. Okay. Now k is discrete, so we don't put k as a continuum variable like we put for phi xt. In Fourier space, it is phi k. Now, this equation is a ODE. Okay, for every k we get a ODE. Okay? So we have lots of ODEs. We can solve these ODEs. We can use Euler, RT2, and so on. So this is just straightforward. Okay. It turns out it has exact solution. We don't need to use numerical methods for this. We can simply solve it with no problem. That's what Fourier did, in fact. Okay, so in 1800, I think 1807. So, but I will illustrate how to use numerical method to solve this equation. Okay, so if I use, let's say, Euler method, then it's going to be phi k at t plus delta t equal to phi k at t plus delta t times right hand side. So minus kappa k square phi k. Okay, this Euler explicit or Euler forward. Okay, and given initial condition, so if I give an initial condition in real space phi x t equals 0, then I can compute phi hat k at t equals 0. Okay, and using this I can time advance. Okay. So this is a code which is a pretty simple code. So kappa equal to 1. Just take kappa equal to 1. T final is 1. We choose 64 and n equals 64. That means Fourier modes will go from minus 31 to 32. So that is a Fourier mode. Since phi is real, k will go. In computer we'll save k from 0 to 32. So we'll use RFFT, okay, real Fourier transform. Now J. So we first discretize in real space. Okay, so we have this basically we discretize my real space into 64 grids points, 64, and at each gauge point I have real space field. Okay, that we need for initial condition. Okay, so initial condition is given here. It is exponential minus 2x minus 5 whole square. Exponential minus 2 times x minus 5 whole square. And the box is 0 to 2 pi. So you can see that this is a function which is peaked around x equal to pi at the mid value. Okay, and so this is the initial condition. Now I need initial fk, right? For my program, I use f and fk as my variables. So there's a Fourier space, a real space, and this Fourier space. So fk, what do I do? I just use Python's RFFT. Okay, so Python RFFT, I just plug in f as one other argument in n, and I get fk. Python does not divide by n, right? So in my definition, I use 1 by n, okay, the sum. So I need to divide by n here. So that's just because of notational differences. That's nothing more. And kx is 0 to n by 2. I just said is 0 to 32 because my field is real. Now, how do I get final state? Since this function is exactly solvable, so if you look at d by dt of f at k is minus kappa k squared f at k. This has exact solution. F at k t equal f at k 0 exponential minus kappa k squared t. Okay, so we just put the initial condition fk coming from here, and the exponential part. Okay, this exponential part is coming here, and that's it. We got fk at time t. Okay. I don't need to use Euler or any of it, and we can do the inverse transform. Yes, for given fk, I can go to ft by just doing IRFFT, and that's it. We have the answer in real space at time t. And this is a solution. At t equal to 0, we had a Gaussian profile at peaking at x equal to pi. And at t equal to 1, okay, at t equal to 1, we get this red. The numerical value is a black one, sorry. The numerical value is a black one. And the exact f is a red one. Okay, the exact solution, which was done by Fourier, so you can easily solve it. It's there in the book. So if okay, so the slight difference at the endpoints. Okay, why? Because the exact solution assumes the function to be till infinity. Okay, so that is till infinity. The box is infinite, and that's when there is some error in numerical one and exact. Okay, so that's the solution. dt, I think, is 0.01. If you choose small enough, you don't need dt. For this problem, we don't need dt because I'm not doing time advance. Okay, great. Now, okay, we are not doing any time integration for this problem, but still, let's try to get some limit on dt. What is the minimum dt we require? So this is my equation. Now, in Euler forward, that's where I will estimate delta t. So Euler forward, the time stepping is this, phi k n plus 1, which is t plus delta t, equal to phi k at t multiplied by 1 minus kappa k squared delta t. Okay. Now, you see, I want this term to be, the prefactor to be less than 1. Modulus of this to be less than 1. Mod of this will be less than 1. And if you choose large enough delta t, that won't be less than 1. Right? And this we did it in the past. So the limit on delta t is this, is 2 by kappa k squared. Okay. But one more point, there are many k's, right? So k goes from 0 to n by 2. So delta t is not 1, it's a multi-scale problem. There are evolution at different time scales or different length scales. So delta t depends on k. So what is the minimum delta t? Minimum delta t is when k is maximum. So that corresponds to delta t min. equals to 2 by kappa K max squared. And we discussed that what is K max? Lambda min equal to 2h. Okay, so that gives us estimate on what should be K max. In fact, you can see from here, K max is n by 2. So that's what I got it here in terms of h, if you like, or n. So delta t is this. 2h squared by kappa k or kappa pi squared. Now, if kappa is very large, kappa large or very large, then delta t becomes very tiny. Okay, that's one of the problems. Let's say kappa is 10 power 6 or 10 power 8, then delta t becomes pretty tiny. Of course, we get some compensation from this small h, but large kappa has issue.